Hey guys, we are going to move into our study of 10.3. 10.3 is going to be talking about how to relate the linear, straight line, and angular variables. So we're going to talk about how much linear motion something would do, and it's doing it in a circle. So think about a merry-go-round and how the horses move. There are horses closer to the center, and there are horses further away from the center. Now every horse moves in the same angular speed. So like the angle that they're changing in reference like circular, that's the same, but very, very different in their linear paths. That's why if you feel like different, right? Like if you're going in a smaller circle, you're not going in a, like if you were to lay that circle out in a straight line, it's not going to be as big of a line if you're going in a bigger circle. So even though like, let's look at the merry-go-round from the top, like there's the center of the merry-go-round. If there's one horse going like this, and then there's another horse on the outside going like this, okay? Every horse is going to have the same angular speed because like no matter where they're at, like the angle and the angle that's changing, the amount of time that's changing is the same. But you can see that this guy does not travel linearly if you laid that on a straight line as far as that one, because the one on the outside has gone farther. We are going to, all the formulas we talked about today are going to use radians, not degrees. Okay. The two sets of variables we're going to talk about r. Let's talk about what r is. R is what you think it is. It's the radius. The two sets of variables are related by r. The perpendicular distance from the point of rotation and its rotation axis. So guys, like this rotation axis will be pointing out at the screen. There would be a right angle with this right here. So this would be labeled as r, okay? The radius, in other words. It is also the radius of the circle traveled by the point around the axis of rotation. So looking at a top view, there's the axis of rotation pointing straight at you. And perpendicular line would go here, perpendicular line would go here, perpendicular line here, here, here. No matter where, if this is coming straight at you like this, all of those lines that I drew down there are perpendicular. So there's just the radius, okay? That's like a point is traveling. Okay, let's talk about what position is. If a reference line on a rigid body rotates through an angle theta, a point within the body at the position r from the rotation axis moves a distance s along the circular arc, where s is given by theta r. Now I'm going to pause the video and make sure I understand the next part I'm going to read to you. So now what we're going to talk about is we talked about position, okay? Like this S and this R are position, one's angular and one's linear. Let's talk about speed now. So that title, I guess, really should have belonged on the top of the screen. What's up, Lily? It's okay. Okay, so here's speed, right? Well, so we know that like speed is the derivative of position, so with respect to time. So if we did like ds over dt, see how it says like we can differentiate the previous equation with L held constant. But if we go ahead and change this s out, we can do that it's d theta times r over dt, because look, there's our theta r. And what's kind of neat is we know that this right here, what I just put a box around, like the change of theta over the change in time, like that is angular velocity. So long story short, if you want to find, if you want to relate angular velocity and linear velocity, you can just take angular velocity times the radius and you'll get the velocity overall. Okay, sorry guys, Lily needed me. If the angular speed of that little w guy of the rigid body is constant, then the linear speed is also going to be constant. In other words, if the angle is changing constantly, then the distance you're moving around that circle is also constant. Hence, the body itself, like you on the horse, will undergo something called uniform circular motion. So the period of revolution, capital T, of motion of each point is given by, and I'm pretty darn certain we did this, 2 pi r over V. I'm pretty certain we had that formula before when we were talking about uniform circular motion. But what's kind of cool, guys, is since we know some stuff here, we can replace. Okay, and wait, hold on. I was gonna make another concept. Do you guys remember like old school? You remember like distance equals rate times time? Like that's really old school, right? So if I was like, hey guys, can you solve for time? You would say distance over r, right? Well, isn't distance 2 pi r because it's their circumference, and isn't r the rate at you're traveling? So it's kind of neat. Like this really does refer way back to these old equations. Time is always distance over rate. Anyway, just wanted to draw that little conclusion for you. Also, let's take a look at this one. I just read the notes over and it made sense to me. I just wanted to make sure it's clear to you. So we can replace velocity, right, with angular velocity times r, which is, so we can definitely use this formula too. Now let's keep going. We can also look at this if we have angular velocity as, you ready for this? So if I write t equals 2 pi over angular velocity, you might be like, you kind of just cheated. Like, how did I do this? Okay, well, for my very, this takes a lot. If you guys move this r to the other side, you have v over r, right? So if you want to replace r over v, w would just go on the bottom. And you can work that out algebraically, but that also proves right here, doesn't it, that those two r's cancel. So both of these formulas reduce to the same thing, right? Angular speed, which is super cool. At least I think so. All right, give me a second. Okay, I'm back. I must be getting better because that one made a lot more sense real fast to me. So we know acceleration, right, is dv over dt. We learned that way back, chapter 2, right, where you take the derivative of velocity to get acceleration. So what's kind of nice here, if we want to replace that v with angular velocity times r, look at that. Here's my r, keep dt. I haven't really changed anything by doing that. And what do we know this as? What did we learn in the last section? What's the change of angular velocity due to the change in time? That's acceleration. Or at least I should not say just acceleration. I should say circular acceleration. Why am I having so much trouble with that word? Let's read this. This leads to a complication. dv dt represents only part of the linear acceleration that is responsible for changes in the magnitude v of the linear velocity, blah, blah, blah. Like v, the linear acceleration, a tangent, is the point in question. There's a lot going on here. It's like blah, 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 blah. Let's just go ahead and focus. This is called the tangential component of the linear acceleration. So we write it like this. We got acceleration based on time, angular acceleration times the radius, or like radius is in like the point away from the perpendicular axis. Okay, let's take a look at what else we can write here. Give me a sec. Oh no, we learned this a while ago, didn't we? We know another formula for acceleration was v squared over r. This was talking. And this should be a little r, not a t. Sorry, r. Acceleration based on the radius is v squared over r. But if we know v can get replaced with angular velocity, we can just do like this little trick. Bump, 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 bump. Right? And then we can cancel one of those r's. So we get angular velocity squared, r. And like you can research all this and try to make heads or tails, but guys, we got a lot of formulas going on. Are you ready? One of the formulas I think is a huge takeaway, linear velocity and angular velocity and how they relate. Linear acceleration and angular acceleration and how they relate. Acceleration here, based on what we have. And really, I mean, we got enough to get us started. If we read through, I think the more we read all these words, we're going to get more confused. We can. Definitely next year I need to take a little more time. But let's just go ahead and punch out some formulas and see. So let's make some heads or tails out of these things. Okay, everybody. So you're going to enjoy this. I had to go to dictionary.com just to be able to read the next problem. Are you ready? In a... Oh, no, it's not doing it. Microhematocrit centrifuge, small samples of blood are placed in a heparinized capillary tubes. The tubes are rotated at 11,500 RPM with the bottoms of the tubes 9.07 centimeters from the axis of rotation. Find the linear speed and the bottom of the tubes, like right here. What is the centripetal acceleration at the bottom of the tubes? So the one thing we definitely need to identify is that 11,500 is revolutions in a minute. That's not okay. In order to take care of that, we need to change this to radians. So there are 2 pi radians in 1 revolution, and there are 60 seconds in 1 minute. We did this in a previous lesson, I think in 10.1. So let's go ahead and change this to a decimal with 4 significant digits. So the tops, 11,500 times 2 pi, that's my top, divided by my only thing on the bottom is 60. So 1,204. So 1,204, and we're going to call this radians per second. So what we just found is the angular velocity. So we had to get it out of revolutions per minute. So let's go ahead and write given. We are given that the angular velocity is 1,204 radians per second. So this was bad, we had to get rid of that. Now the fact that the bottom of these tubes is 9.07 centimeters from the middle is fine, but centimeters is not good. So we'll do R equals 9.07 centimeters divided by 100 is 0.0907 meters. Now part A, find the linear speed. Linear speed is just V. So we go back through, we find our linear speed right here, angular velocity times R. Lily's outside, Nate. So that's going to be angular velocity 1,204, radius 0.0907, calculator. I think this is really cool, by the way. I don't know if any of you do this, like I donate blood, but I'm too lazy to donate plasma. Actually, I mean, it's so much time. You just sit there for like 3 hours and they spin your blood so fast that it like pulls the plasma for it. It's an awesome, and it's an amazing life-saving opportunity. If any of, I'll do it when maybe, you know, I have a little more time on my hands, but 109.2. And since we're now in linear velocity, that's meters per second. So you're saying, what if you could lay it out on a straight line? If you could take your circle and lay your circle out on a straight line, how fast is it going on that circle? It's going 109.2 meters in 1 second. So just so you know, that's really fast. Hold on, give me hey Google, how many miles per hour is 109 meters per second?
109 meters per second is equal to 243.826 miles per hour.
That's really fast, guys. So it's over 200 miles per hour. Thanks, Google. All right, I'm going to take a look at part B. I'm solving this on the fly just because we're a little pressed for time, so give me a sec. Okay, so they want the centripetal acceleration. I kept calling it angular acceleration. Will you please forgive me? It's centripetal acceleration. No, I'm good. Angular acceleration was good. I'm sorry. So they want the centripetal acceleration, so that's going to be this one right here. All right. So we can't, like, this one's not going to be helpful. We want this one. We want this one right here because we have angular velocity squared times r. You ready? Let's do this thing. So I can say my centripetal acceleration, boink, that's in centripetal acceleration, is equal to v squared over r. That was part of the formula, right? And we also calculated that that's angular velocity squared times r. So what's neat is you can really do either one. We're given both, so I just want to prove that. I'm going to choose to do this angular velocity one because it was the least rounded. So 1,204 squared times r 0.0907. Let's take a look at this. We don't need parentheses for the square because it's not negative. So I'm calculating a lot. You ready? So that's 131,480, and I have 5 significant digits on that, but I'm not going to fix it. Meters per second squared, which is pretty darn awesome. That's the force of acceleration, the centripetal acceleration, which is absolutely amazing. You could, I do want to prove to you that it's going to be just a tad bit off. Here, let's make this 4 significant digits. So this is actually going to be a 5 and a 0 instead of a 4 and an 8. Okay, you ready for this? I want to prove that you could do this one as well. So v squared would be this divided by r. And if you guys take a look, 4 significant digits is the same because it would be 1315, and it's just off because we did some rounding throughout our problem. So that's pretty nice. I love seeing it, like when you can use more than one formula. Next problem, I'm going to read it. Okay, I don't see any words I need to go to my dictionary for. Suppose the centrifuge in the previous example is starting up with a constant angular acceleration. So that's that funny looking A thing. And there, I'm going to write that because that's given and I don't want to lose that. So I'm given funny A thing is 95 radians. Good. I'm glad it's radians, and second squared, no weird stuff to convert. What are the magnitudes of the centripetal, the tangential? Okay, so we have 2 different accelerations, right, guys? This is that t. Did I say time earlier in the video? So if anybody wants to just like call me up and tell me I'm stupid, that t would be tangential. I'm going to put that in there for next year because next year I'll be smarter. Tangential. And this r stands for radial. I apologize. Please forgive me. Okay, so now I'm going to go back to the question. Hey, we all make mistakes, clearly. What are the magnitudes of the centripetal, tangential, and total accelerations of the bottom of the tube when the angular speed is 8 radians a second? Ooh, are you ready for this? So let's start by finding the centripetal. Okay, so that would be formula, that's messy. W squared, r, angular velocity squared times r. So they want us in part A, they want the angular speed to be 8. So I understand that up here we were looking at the angular speed elsewhere, but they're saying what if the angular speed is 8? Okay, let's go ahead and solve if it's 8. Here we go. So it's starting up and it's gaining speed, and we're at 8 radians a second. So we're just going to plug in 8 squared. Thank goodness the radius is not changing because it's the same centrifuge. Let's plug that puppy in. Mr. McBurney has 5.8, so let's hope that we're good with him. I hate doing problems on the fly. That's good. For significance, 5805. 5805. 5805. Forgive me for I usually solve these on the side first and then come back to you. I just don't have the time today. I'm sorry, guys. And that would be meters per second squared. All right, what else do we need to find? We need to find the tangential. So that would be A sub t, and we know that's, let's see, angular acceleration times r, I think. Let's take a look back here. Is that how we wrote it? It sure is how we wrote it over there. So the angular acceleration they are giving to us. Now remember what we're doing, guys, is we're comparing a linear acceleration to a circular. Yeah, you can you make me a cup too? Please? I'm getting a cup of coffee, guys. So let's put in 95 radius. Oh, I love it. I love it. I love it. I feel like after we're done with this example, I might go on Google and just kind of do a quick search on what makes these two so different. And I would encourage you to do that too. That would be something that if I was teaching the classroom, if I was teaching this in the classroom tomorrow, I would look up. All right, so 8617. Decimal after the 8. And this is tangential, so we're talking about meters per second squared again. All right. And let's keep it up. Okay. A total. Ooh. So let's go ahead and write. I didn't see this in the notes, so this is a learning moment right here. It asks you for the total acceleration. So to find the total acceleration, we are going to, we're just going to call it A, and it is going to equal, must be a hypotenuse. I'm going to need to look that up again. Take a look at this formula, write this formula down. I don't believe that formula was found anywhere in the notes. And it is because theta, if we did tan of theta, if you look at this right here, I think we can reason this through. Can I zoom in? I cannot zoom in, but I can move this down and make you dizzy. Okay, are you ready? So they're saying if something's moving at an angle like this, tan is opposite. Wait, we know tan of this little funny thingy, not theta, whatever beta, is equal to the opposite over the adjacent. And the opposite of this little angle is your centripetal acceleration. The adjacent is your tangential. So centripetal acceleration pulls it in. Tangential acceleration is if like you let it, how fast it's accelerating, like in the actual, if you were to let go and go bing. So acceleration tangential. So if we know that, then we know the total acceleration would be the hypotenuse, which is why we can do the Pythagorean. I hope I made sense out of that. If not, like, just let me know. Maybe we could talk a little bit more about it in a video or something. All right, so let's plug this stuff in. So AT squared, we're going to do 8.617 squared plus 5.805 squared. I'm going to take the square root of that stuff. Let's plug that in. 8.617. You guys are like, I got this. I remember how to do this. So 10.39 is your total. And that's going to be in meters per second squared. Okay, all right, so we have all of these. I no longer need to Google the difference because we have a very beautiful picture of what the difference is of those two right over there. Let's see, part B, what angle? Okay, so what is the angle? So what's that little guy right there? Between what angle does the total acceleration make with the direction of the motion? So they're asking about this angle right here. Not a problem. We can do the inverse of tan of the opposite, which is AR, over the adjacent. And let's just double check, make sure. Oh, and this is actually going to be in degrees, which is fine because we're not talking about angle, like the circular one. We're talking about the difference between the two. Ready? Second tan, 5.805 divided by 0.617. There it is, 3397. Awesome. So that is the angle that the total acceleration makes with the direction of motion. Very exciting. All right. Sample 3. An athlete whirls a discus in a circle of radius 80 centimeters. I'm going to write that down as a given. R equals 80 centimeters divided by 100, boom, boom, which equals 0.8 meters. At a certain instant, the athlete is rotating at 10 radians per second. That in the angular speed. So that sounds like it's like its original angular velocity. Let's see if we like this. If I write this down and we'll kind of go with it. Thank you. And that is going to increase with an angular acceleration of 50 radians per second squared. At this instant, find the tangential and the centripetal components of the acceleration and discuss the magnitude of the acceleration. All right, so we don't have part one, we don't have part A, part two. We're just going ahead and solve each one of those. Now, if you want to, I'm going to pause the video and make sure I know how to solve each one rather than just do it on the fly. I think we have everything. The answers are 40, 80, 89.4. So I'm just going to double check, make sure I'm good, and I'd like you to do the same, please. Okay, guys, it's actually a lot easier. I don't know why I was having a moment. It's formula. So the tangential acceleration, like if you let go and it went in a straight line, is this, and the radial is, which might be easier to do this. Both of those are usable, but this one's going to be a lot better. And then this one's going to be the hypotenuse of the two. So let's see. Angular acceleration, so we'll do 50 times radius of 0.8. Silly me. That's, of course, where he got his 40. This is tangential, so it's moving in a straight line, so meters per second squared. This one's going to be angular, which is 10 squared times radius of 0.8. That's where we're getting our 100 times 0.8, so 80. This is centripetal acceleration. So again, we're talking about meters per second squared. And that's just at this exact moment. I know it's increasing, but we're just asking about this exact moment whenever we're going 10 radians a second. So the overall acceleration, we are going to talk about, we're going to do 40 squared plus 80 squared. I didn't double check, I just assumed I knew what I was doing. Mr. McBurney got 89.4. 89.44, we did good. Meters per second squared. So it's kind of neat. And I think the important thing for you guys to understand is, hold on, I'm having a moment. Trying to get the important stuff here in a box. That you can use angular motion to help you relate it to its linear path that it would be traveling if you laid it out on a straight line. Now, example 4, Mr. McBurney did not solve. I may possibly solve it myself and then Google it real fast to make sure that I got it right, and then just walk you through it or give you guys the link for it. I miss you terribly. I'm sorry that this seemed like really kind of pieced together. I hope it made sense. The main idea is how to relate linear motion to angular motion and how one motion can help you predict the other one. Hopefully I'll find some really good examples for you, but I'm going to get example 4 done. All right, just a sec. Okay, guys, this problem brings a lot to the table, and I realized when Mr. McBurney did not solve it. This is way more difficult probably than anything that we really need to venture into, so if you just want to pause the video and not listen, you can do that. The first thing I did want to make mention of is the blade tips. Oh, I don't know if I read it. You're designing an airplane propeller that's going to turn at that 2,400 revolutions per minute. The forward airspeed of the plane is 75 meters per second, and the speed of the tips of the propeller blades cannot go any faster than 270 meters per second. What is the maximum propeller radius? With this radius, what's the acceleration of the propeller tip? So the first thing we need to do is understand this blade tip speed. Right away when they added that extra, hey, the plane's also going like 75 this way. So the tip of the propeller, so remember, it's spinning like this, which is a speed, right? Like, which has a tangential velocity. So here it is, we're spinning like this, but not only does it have that tangential velocity, it also has 75. So if you picture, see my finger, this is that my fingernail is just the tip. It's a little itty bitty dot on the very end of a propeller blade. So I have tangential velocity right now. If I let go and I went in a straight line, I would have some velocity. But now think about, ready, here I come. Now my tip of my finger is moving even faster because we have to accommodate for that 75. So the long story short is they have a really pretty picture here. The overall velocity of a propeller is the hypotenuse between its forward motion and its rotational motion, because it's, here and here. Like if I'm spinning in a circle, I'm going this way and I'm going this way or this way. Anyway, it doesn't matter. You're going in, you have like this up and down or up and down with the left and right. So thinking about that, the total velocity is the hypotenuse, which is the square root of the two things squared. So the one we know is 75 squared. That's this way. What we don't know is this. Okay, we don't know the velocity of my spin right now. So let's go ahead and get rid of that 2400 RPM. That's not good. So 24 RPM converted into 2 pi radians, 1 revolution, 1 minute, 60 seconds. This is the angular velocity. This is a very important number. The angular velocity is 251. That doesn't change. Okay? The reason that doesn't change is because this doesn't change. So anytime we use a formula for this particular plane, like this one up here, see that angular velocity? That's 251. We don't know the radius. We also, this velocity here, that's the spinny velocity. That's not the overall velocity. Okay, do you like that I use the word spinny? I feel like that makes me sound incredibly smart. So they said that the total speed of that tip of the plane, this speed and this speed, has to be 270. So you see where it says V total? I replaced it with 270. There it is. And we knew that that's the hypotenuse. So the hypotenuse is equal to the square root of the squares of the sums of the sides. So we know 75 is its forward motion. What we don't know is its circular speed. Okay, tangential velocity. Whee! So we're going to do some simple algebra. We're going to square both sides, and we're going to subtract and take the square root. That gives me, if you want to see it played out, here's how it works. It's 270 squared minus 75 squared, and the square root of that answer is 259.4, and that is for my my linear velocity of my circle. Okay, maybe you just want to write linear velocity of the circle. Like if you could lay the circle out, it's how fast the propeller's rolling on that circle. Okay, that's fast, by the way, and this is in meters per second, not in radians per second, because I'm talking about how fast the pencil's moving, like on a straight line, if the circle was a straight line. Okay. Now I had a point. Okay, so this is the circular velocity, right? Like if it was traveling on a straight line, which is that V right there. So I'm going to do V equals angular velocity R. Now this is just the V for the circular motion. So that's 259.4 equals angular velocity 251 times R. So that tells me my radius. Okay, I'm going to grab my calculator, divide by 251. And that tells me that my radius is only allowed to be 1.033 meters. Great. So we got part A done. I thought that was pretty exciting. So everything above this line was given. Everything below this line helped me solve for part A. Now for part B, gotta pause the video. All right, I'm back. So it says, what is the acceleration of the propeller tip? So again, you might be thinking like, oh man, I've got acceleration like this, I've got acceleration like this, I've got acceleration pulling me in, I've got acceleration around my circular, I got centripetal acceleration. What acceleration do they want? Well, what's kind of nice is the acceleration, the only acceleration acting on this thing, first of all, it's going a constant 75, so there is no acceleration on this 75. So you can completely ignore the fact of the forward moving 75. That's constant. There's no acceleration there. Also, it says that it's not accelerating in my circle. It says it's going 2,400 RPM. That's a constant. So we don't have that acceleration to deal with. The only acceleration we have to deal with is centripetal acceleration in this particular problem, which is AR, which is, I think we can just, I don't think I need to find all my formulas. I'm pretty sure that one's the only one we need. Because, yeah, we have angular velocity of 251, and we have a radius of 1.033, and my husband's going to be so proud that I'm done. 65080 meters per second squared. It's centripetal acceleration, so that would be like a linear label. No, linear label. That was fun for me to say. I'm just going to double check with this website, make sure I got the same answer they did. Oh, great, I lost it. Good for me. Just scrolling through. Sorry, guys. They have 6.5 times 10 to the 4th. 1, 2, 3, 4. Yes, we match. So yay, we did it. That was a neat little problem. Again, that particular one was a little more intense than what we probably needed to get at. I am missing you guys like crazy. And again, I'm sorry that this was very like pieced together. Oh, look, one of my youth group kids had a question. She's in 9th grade, guys. Look, she's in 9th grade, and look at what they have them doing in algebra. This, that'd be awesome. You know what you guys should do, my physics kids? You guys see everything right between my fingers there? That's what she was given, and she had to solve it. She had to reduce it. That'd be awesome. That'd be wonderful, wonderful, wonderful algebraic for you guys to do, just for fun. I know, it is fun. All right, have a lovely day. Missing you terribly.